The question is, find an expression, find an expression for the series is given 1 plus 3 plus 5 plus 7 few dots for the first n terms. For the first n terms. So the series continues up to n terms. N is unknown. What is the first thing? We have to find our general term or common term. Can you remember the steps? Take the difference. Difference is 2. Multiply that by r. 2r minus 1. 2r minus 1. This is the general term. Now how to write? How to write that sigma notation? R equals 1 to n 2r minus 1. Because we want the sum, we have plus in between terms. So it is summation. Sigma r equals 1 to n, and have to write the general term 2r minus 1. Now we can apply the characteristics of sigma notation. We can divide this 2r minus 1 from this minus mark. That is 2r minus 1. And take the common, take the coefficient 2 out. Okay, this is how we can write the second step. Take the coefficient out, r, and separate from minus mark and write a different sigma notation. Now apply the theory. 2 times sigma r equal 1 to n r. From previous theorem we know it is n by 2 into n plus 1 minus sigma r equal 1 to n. 1 is n. Okay.
Yes, sir.
Now simplify. Cancel 2. We have n square plus n minus n. N get cancelled. Answer is n square. Okay, then there is another method. Actually, this is method 1. We can apply the last theory we discussed in previous session. What was that? It is like this. We have to rewrite or rearrange this series given like this. 1 plus this. In between, I can put the missing digits 2, 4, 6, and here we have 8. I have written the missing digits. Then what is this? Sum of first n terms from 1 to n. Now this is a different series. Here the difference is 1. Earlier case, the difference was 2. Now for this sigma notation, what is the general term? It becomes r. It is not 2r minus 1. Because I have 1, 2, 3, 4. All the counting numbers. General term is r. But there is a small difference for the r equal 1 to n thing. The two boundaries. Starting number is 1. In this particular series, which was given in the problem, they asked for first n terms. That means first term, second term, third term, fourth term up to n. Okay, let's say we have our n term here. Our n term is here. So we have n number of terms. First term, second term, third term up to n. Now when I fill 2, 4, 6, 8 in this manner, what will happen to the number of terms in this series? When I fill these missing digits, what will happen to the number of terms in this series? Will it going to increase? Yes, it's going to increase by the same amount. Here we had n number of terms. When I fill these missing numbers to the middle, then we will get another series having n number of terms. This series had n number of terms. Now this is also having n number of terms. Then altogether we have 2n terms. That is the point that you should carefully change in your sigma notation. It is not just r equals 1 to n. Here it is r equal 1 to 2n. Understood?
Yes, sir.
Okay. Now, the question had 1, 3, 5, 7. I put 2, 4, 6, 8 additionally. Now, I have to make that correction. These additional terms must be subtracted. These additional terms must be subtracted. Now we have to consider this blue color series 2, 4, 6, 8. 2, 4, 6, 8. What is the common term for that? Is it 2r? Yes, even number series. Common term is 2r. Then what is the summation? R equal 1 to n. Because this series is having n number of terms. Then we have to subtract that particular sum. Sum we will get from this blue color series. What is that? R equal 1 to n 2r. Understood?
Yes, sir.
Sure, right? If not, tell me.
Yeah, sure.
Okay. Now we can directly substitute. What is the from the theorem? You know the summation for r, that is n by 2 into n plus 1, isn't it? But this is when r equals 1 to n. This answer we got when r equals 1 to n. Now we have 2n. Therefore, I have to replace n by 2n. That is the only difference. When we have 2n, you have to replace that by 2n. Then here, we can take this 2 coefficient out and write our answer. Sigma or summation for r, what is that? N by 2 into n plus 1. Here in this case, we have 1 to n. No need to change anything. This 2 is the coefficient. Now cancel 2, 2 get cancelled. N into 2n is 2n square plus n into 1n. Here n into n square, that is minus n square. N into 1n, that is also minus n. Minus n plus n get cancelled. 2n square minus n square, answer is n square. See, we get the same result. This is easy. But sometimes in the question, in the paper, they may guide us to get the answer in this form. In the question, they may change this and say use this kind of format. Then you have to use this. So 3.1, 3.2 were based on our first theorem. What was the theorem? Sigma r equal 1 to n r. Answer n by 2 into n plus 1. Now the second theorem. Second theorem is sigma r equals 1 to n r square. That is equivalent to n over 6 into n plus 1 into 2n plus 1. This is the theorem. So you should keep this in mind. Then what can be the series here? Series is in this form: 1 square plus 2 square plus 3 square 4 square, like this. Because here we have r to the power 2. Each and every term should be squared. Then sum of this kind of a series is n over 6 into n plus 1 into 2n plus 1. Okay, then the proof. For the proof, we have to consider similar equation like what we used in previous theorem. This is, in earlier case, we used r plus 1 square. Here I have to use r plus 1 cube. Okay, and you have to write the cubic expansion. What is the cubic expansion? R cube plus 3r square plus 3r plus 1. This is cubic expansion. And you have to rearrange. Write these three terms in left. 2r. R plus 1 cube, and send r cube to that side, minus r cube. Now this is the equation that we are going to use. Okay, now substitute from 1 to n when r equals 1. When r equals 1. Now I'm going to write it quicker. 3 into 1 square plus 3 into 1 plus 1. Then substitute 1 here. This becomes 2 cube minus 1 cube. If it is not clear, ask me. 3 into r equals 2. 2 square. 3 into 2 plus 1. This is 2 plus 1, 3. 3 cube minus 2 cube. Then can you see? These two terms get cancelled when we take the sum. They are going to get cancelled. So 2 steps from top is enough. 2 steps from bottom. This is 3 into n minus 1 square plus 3 into n minus 1 plus 1. I am substituting n minus 1 for r here. Then right hand side I will get n minus 1 plus 1. It is n cube minus n minus 1 cube. Then r equals n. 3 into n square plus 3 into n plus 1. Then here we have n plus 1 cube minus n cube. Now take the sum from first term to nth term. See, these two get cancelled. These two get cancelled. We can clearly identify the pattern. These terms will be cancelled. We have these two terms. Understood?
Yes, sir.
Okay, now take the sum. 3 is a common factor. So it is 3 into what we have here. 1 square, 2 square, 3 square up to n square. This sum. So we are calculating that. Then write the sigma notation. R equals 1 to n. What is the general term? 1 square, 2 square, 3 square means r square. Then here, once again you have 3 as the common factor. Take it out. Then what is the series you have? For the second part, 3 into 1, 3 into 2. Here you should have 3 into 3. Here 3 into n minus 1, 3 into n. That means 3 into sigma r equals 1 to n r. Series is 1, 2, 3 up to n. That means sigma r plus. Here we have only the common factor, common number, that is 1. Then when we add these, we are having only these two terms. 1 cubed is 1. So we don't know the value of this, but we know the values of these. Sigma r is previous theorem, n over 2 into n plus 1. Then sigma r equal 1 to n, 1 is n. The meaning of this is we have n ones. Expand, cubic expansion. Now simplify. Take these two terms to left right hand side. N cube. Take this n. This is minus 3 over 2 n into n. That is 3 over 2 n square. 3 over 2 n into 1. It is minus 3 over 2 n. There is no n cube term. And here we have two n square terms, like terms, simplify. When we simplify these two, you get plus 3 over 2 n square. When we have three like terms, simplify these two, it is 2n. 2n minus 3 over 2n, answer is n over 2. Simplify and see. 2n minus 3 over 2n, that is n over 2. Then take the common denominator for these three fractions. Common denominator is 2. And common factor, you have a common factor, that is n. When we take n out, here we have n square plus n plus 1. Then divide both sides by 3. Then you have sigma r equals 1 to n r square equals, take n out. When we divide this side by 3, denominator becomes 6. Because we get 3. 2 times 3, 6. Then here we have a quadratic equation. Now factorize this quadratic equation. You will get these two factors. I think I made a mistake here. Yeah, when we take the common denominator 2, this should be 2, huh? Because denominator here was 1. So this becomes 2n square. 2n square. Then the factors are n plus 1, 2n plus 1. Expand and see. N into 2n, 2n square. 1 into 1, 1. So this is the proof. Understood?
Yes, sir.
Take a screenshot.
Okay, sir.
Now keep in that theorem, that answer. Let's take 3.3 example. There they have given, find an expression in terms of n for this sigma r equals 1 to n 3r square minus 4r plus 2. So without giving a series, they have given the series notation with the general term directly. So we need to just apply the characteristics of series notation and the theorems. The two theorems we just learned. So r equals 1 to n. we can take this 3 coefficient out and write r square. Then minus 4 separate sigma for that. Then for 2 we can write another separate sigma. So this is the application of the characteristics of sigma notation. Now apply the results you got from two theorems. R square, what was the answer? N over 6 into n plus 1 into 2n plus 1 minus 4 times, what is the answer for sigma r? N over 2 into n plus 1 plus, then 2 times, this is actually 2 times 1, you can write like that. 2 is, take the 2 coefficient out, then sigma 1 is n, and that becomes 2n. Now simplify. Okay, you can take n out. In all 3 terms you have n. Okay, when you have a denominator like this, at least in one term, take that denominator as a common factor also. That is an easy way of simplifying. When you have at least one denominator, take it out. If you have 2 denominators, then take the LCM. Let's say we had 3 here, we have to take 2 times 3, 6 as the common denominator. Here we have only 2, so just 2 is the common factor written in denominator. Then n over 2 is taken out, minus n taken out. We didn't have 2, so we have to multiply the numerator by 2. Then this becomes 4. 4 into n plus 1. Because by force I took 2 out. Then you have to make that error correct by multiplying the numerator by 2. Take n out. Here also we didn't have 2 at the denominator. To make that correct, you have to multiply the numerator by 2. 2 times 2 becomes 4. There is no n. I took this n out. Now simplify. Here we have 2n square plus n plus 2n plus 1. 4 get cancelled. N by 2, 2n square. When we simplify these like terms, we get minus n plus 1. Check whether we can simplify or factorize this quadratic expression. I think we can't. Yes, we can't factorize that further. So this is the answer. Understood? Hello, are you there?
Okay, sir.
Okay. Then another question. Now the series, this is not in your textbook. As an example. Then 1 square, 4 square, 7 square. This is the series. Okay, can you see? Okay, 1 square, 4 square, 7 square. This is the series. then you have to find the sum of first n terms. Here you have to find the sum of first n terms. What is the first step? First you have to write what term? General term. Now tell me the general term for this series. Quickly.
Okay. 3n minus 2 square bracket square.
3n minus 2. Yeah, but yeah, correct, but we are using r, not n. For the final answer we get n. When we are writing general term, we use r. It is 3r minus 2 whole thing square. Now, if they ask to find the sum of first n terms, that is when r from r equal 1 to n of this particular series, so we have to write our general term like this. Then here we have a square. So before using the characteristics of sigma notation, we have to expand this. Sigma r equal 1 to n. What is the expansion? Square this is the expansion. Now we can apply the characteristics. Take 9 out, r square. Take 12 out, r. Take 4 out, it is just 1. Now you can apply the results. R square is n over 6, n plus 1, 2n plus 1. 12 into what is sigma r, n by 2, n plus 1. What is sigma 1? It is just n.
Sir, for the expansion, is it meant to be minus 6 or?
For the expansion, minus
6 or?
minus what?
9
Minus
or?
6. Here.
No, instead of minus 12.
Yeah. What is the middle term? How we get the middle term when we square? 2 into first term into second term. First term into second term is 6. 6 into 2 is 12. Middle term is 2 into first term into second term. Okay?
Yeah. Sorry.
Cancel by 2. Then cancel by 3. Then now we have in common factors. Yes, n. N is common. Then any numbers? No. 3 is odd. Then here we have a denominator 2. Then take the denominator out. So when we take n out and 2, we have 3 times n plus 1, 2n plus 1. Here we have 12 because we didn't have 2. I have to multiply 6 by 2. Here also we didn't have 2. We have to multiply, n is taken out. When I expand, I get 2n square into 3, 6n square. 1 into 1 into 3, 3. 1 into 2 and 2n, n into 1, n. Altogether we have 3n. 3n into 3, 9n. Do the simplifications later. Do this simplification if you can't get this directly. Because I want to discuss the series thing, not the simplification. 12n minus 12 plus 8. 6n square. When I simplify this, I get minus 3n. When I simplify this, I get minus 1. If you can factorize this further and have these kind of brackets, you can get. Otherwise, this is the answer. Check that. Okay, these are the 2 steps that you have to do in series, and also this one, 3 steps. After that, it is just simplification. Okay, understood?
Yes, sir.
Okay, take a picture quickly. I think we have 10 more minutes.
Okay, sir.
Okay. Now I'm going to move to the third and the last theorem. That is for R cube. First one was for R, second one R square. Now this is for R cube. Then what can you say about the series? It should be 1 cube, 2 cube, 3 cube, like that. Then we have to find sigma R equals 1 to n R cube. The result, the answer is, what is the theorem for this one? Can you remember? For R, that was n by 2 into n plus 1. For R cube, it is the square of this result, square of R, that is n square, n plus 1 square over 2 square, it is 4. Easy to memorize. R cube, it is the square of what we got for R. Now how to prove this? So we have to consider our equation. What is that? R plus 1. Earlier for R square we got cube. Now for R cube I have to get R plus 1 to the power 4. R plus 1 to the power 4. Then what is the expansion? Now you should know the expansion for 4th power. Okay. For squares, we know the coefficients are 1, 2, 1. That is first term square, 2 times first term into second term, and second term square. Those are the 3 terms. Then for a cube, what is the pattern? First term square, coefficient is 1. 3 times first term square into second term. Then third term, 3 times first term into second term square. At last, second term square. So these are the coefficients. We have to...
Sir, I can't see what you're writing at the right hand corner.
Okay. So these are the coefficients. There is a triangle called Pascal triangle in order to obtain the coefficients of these higher indices. The coefficients are 1, 4, 6, 4, 1. Okay. How did I get this? That is like this. You know the coefficients you have for binomial expansion of a square. For a square, the coefficients are 1, 2, 1. Then, for the next expansion, for the cube, write 1, 1 either side and take the sum of these two. 1 plus 2, 3. Take the sum of these two. 2 plus 1, 3. Similarly, take the sum. 1 plus 3, 4. 3 plus 3, 6. 3 plus 1, 4. First term, always first term and last term, they are 1. So this is for the 4th index. Then for the 5th, 1, 1. Take the sum. 5. Take the sum. 10. Understood?
Yes, sir.
Yeah, this is what we call Pascal triangle. So these are only the coefficients, are not the English letters. The coefficients we have to write. Then when I write the expansion for R plus 1 to the power 4, we have R to the power 4 plus coefficient is 4. r to the power 3. Coefficient is 6. R to the power 2. Coefficient is 4 plus 1. In the descending order, this index of R is going to decrease from 4 to 1 because here we had R. Okay. First term is R, second term is just 1. Then we have to write only this R term because each and every term is just multiplied by 1. Nothing change. Now take these terms and write in left hand side. That is the pattern. And take r to the power 4 here. Then here we have r plus 1 to the power 4 minus r to the power 4. In previous proofs as well, we did the same thing. Keep in the first term. In this side, I wrote all the other terms in left hand side. Now substitute from r equals 1 to n. Then you will get those terms and take the sum. Then you can get the answer. Okay, I'm not going to do that. So you write these two steps and try to get our final answer. This is the final answer. Simplify and get that answer. Okay, we'll just simplify this and check whether you can get this answer. Did you start? Substitute when r equals 1. This becomes 4 into 1 cube plus 6 into 1 square plus 4 into 1 plus 1. Then when substitute 1 here, this becomes 2 to the power 4 minus 1 to the power 4. 1 to the power 4. Then when r equals 2, 4 into 2 cube plus 6 into 2 square plus 4 into 2 plus 1. Then here 2 plus 1, 3. 3 to the power 4 minus 2 to the power 4. Then when r equal n minus 1. This becomes 4 times n minus 1 to the power 3 plus 6 times n minus 1 square plus 4 times n minus 1 plus 1 equal, substitute n minus 1 here, it is n to the power 4 minus n minus 1 to the power 4. Now the last step, r equals n. 4 into n cube plus 6 into n square plus 4 into n plus 1. Here, when I substitute n plus 1 to the power 4 minus n to the power 4. Now it is clear when I take the sum from 1 to n, these get cancelled. These two get cancelled. Then these two also get cancelled. Then the result is 4 is a common factor. Here we have 1 cube, 2 cube, 3 cube up to n cube. Sum of 1 cube, 2 cube, 3 cube, that is sigma r equals 1 to n r cube. General term is r. Then plus 6 times, what is this? 1 square, 2 square, 3 square, up to n square. Then it should be r square. 4 times 1, 2, 3 up to n. That is sigma 1 to n 1. 1 to n r. Here we have 1. How many ones? N ones. That is sigma r equals 1 to n 1. Right hand side we are left with n plus 1 to the power 4 minus 1 to the power 4, which is 1. This is what we are finding. We can substitute these things. 6 times r square. What is the answer? Sigma r square n by 6 n plus 1 2n plus 1. Then here 4 times sigma r, that is n over 2 n plus 1. Sigma 1, that is n. Now expand this to the power 4. Once again, same coefficients 1, 4, 6, 4, 1 from Pascal triangle. Pascal triangle. N to the power 4 plus 4 n to the power 3 plus 6. 6 n to the power 2 4 plus 4n plus 1. Last term is 1. Here minus 1. Minus 1 plus 1 get cancelled. Now simplify. 6, 6, 2. That's all. Now expand these brackets and send those terms to right hand side. Here we have n 4, 4n 3, 6n 2, 4n. Expand these two brackets. 2n square into n, that is 2n cube. It is positive when it goes to right hand side, becomes negative. And last term 1 into 1 1 into n, that is plus n. When it goes to right, it becomes minus n. Then what are the middle terms? 1 into 2n, we have 2n term. N into 1, n. Altogether we have 3n. 3n into n, that is 3n square minus 3n square. Then here this bracket 2n into n, 2n square minus 2n into 1, it is minus 2n, plus n becomes minus n. These are the terms. Now simplify. n4. We have two like terms. When we simplify, we get 2n to the power 3. We have three like terms. Simplify. Plus 6 minus 3 plus 3 plus 3 minus 2 plus 1. Then plus 1 n square is n square. Then these are also like terms. Minus n minus 2n altogether minus 3n. Minus 3n minus n minus 4n. Minus 4n get cancelled with plus 4n. All the n terms get cancelled. Here we had 4. It becomes denominator. When we can take n out, n square out from these 3. N square over 4. Within brackets we have n square plus 2n plus 1. When we take n square, we are left with 1n. When we take n square, it is just 1. Now can you see? This is n plus 1 whole thing square. n plus 1 whole thing square. N square 2n plus 1. This is the answer for R cube. So this is the proof. So you should do these proofs at least 2 times and be prepared. Sometimes you can get, but the calculation is very important because the same logic must be applied for the next chapter, that is for 3.2. The same simplification procedure must be applied for 3.2 problems. Okay, that concludes 3.1, and